Okay, here's another linear equations video, and this one is on the exceptions in y equals ax plus b. I'm going to explain what I mean. So in our last video, we learned about how a straight line on a Cartesian plane could be defined by an equation y equals ax plus b, where a is the slope and b is the y-intercept. This video is going to focus on what happens if there's an exception there, like what if it doesn't quite look like y equals ax plus b. And yes, there are a few cases where that's going to happen. And we're going to look at those exceptions over the next couple of minutes. So first of all, what if I don't see a number where I'm expecting to see slope or y-intercept? What do I do then? Now we'll start off with slope. So what if my equation looks like y equals negative x plus 2 or y equals x minus 8? I don't have that number out front of x that represents slope where I'm expecting it to be. Well, the explanation here is actually really easy. When you don't have a number in front of a variable, it's like there's an invisible 1 there. So in the y equals x minus 8 example, out front of that x, there's an invisible 1. So the slope of that line would be 1. And in the y equals negative x plus 2 example, because it's negative x, there's an invisible negative 1 out front, meaning the slope of that line is just negative 1. So now what happens if I have a line that doesn't show a b value in the equation, like y equals 0.5x or y equals negative 3x? What do I do then? All this means when the b value is completely missing is that the line passes through the origin. The b value is actually 0 there. So I could rewrite the first equation, y equals 0.5x plus 0, and the second equation could be rewritten as y equals negative 3x plus 0. So these two lines actually do have y-intercepts. It's just that because we're, kind of lazy by nature, if the y-intercept is 0, we don't bother writing it. So it's understood, though, if a line doesn't have a y-intercept in its equation, like one of these two, that those lines actually do pass through the origin. They do have a y-intercept. It's just 0. Now, it is possible also that an equation is missing the x or the y value in it. Something like y equals 10 or x equals negative 8. And these special cases are used to represent perfectly horizontal or vertical lines. Now let's look at y equals 10 first. If I got an equation that just said y equals 10, what I'd be looking at here is a line, and all I know about it is that it passes through a y value of 10. It's perfectly horizontal. And if you think about it, the definition of the line being y equals 10 is actually pretty appropriate here. The x values range from negative infinity to positive infinity. So x could be anything. And the only thing I need to define my line is that I know the y value is 10. And it's always 10. It never goes up or down from there. Hence the equation y equals 10. Now a similar rule applies to x equals negative 8. If we look at the line through x equals negative 8, the y values vary from negative infinity to positive infinity. But the x values never move left or right from negative 8. So while y could be anything, on this line, x is always negative 8. And the equation, x equals negative 8, makes perfect sense. Now, one last thing I need to mention here is that sometimes you might get an equation that doesn't quite look like y equals ax plus b. It's a complete equation, but the numbers don't seem to be in the right place. So it might look like this or this. And anytime we see either of these equations or anything that looks like them come up in this course, we're going to stop right there in whatever question we're working on and isolate the y variable. Because when we isolate y, the equation is going to look like y equals ax plus b. Now remember, isolate just means to get something all by itself. So in each of these equations, I'm going to isolate that y variable and see if the equation makes more sense once I do that. And now that it's done, I can see the slope and the y-intercept of each line, meaning the definition of the line is a lot more clear now that my work is done. So now check out a couple of examples on exceptions in y equals ax plus b and how they might pop up in test questions.
Hey guys, welcome to Exceptions in the Equation of a Straight Line instructional video. Which of the following equations correctly defines the line shown in the graph below? So Sometimes, usually, I should say, more frequently, we get lines that have what we call a slope or a rate of change. And we've seen lines that look like my pencil here that are growing lines, whether they have an initial value way down here, and whether they're very steep or they're very flat, or whether the initial value is up here somewhere and they're very flat or really, really, really steep, whether they're positive or whether they're negative. If you imagine this is a ski hill, that would be pretty terrifying. That would be pretty boring, right? But certainly either way, they're sloping down, negative slopes. Sometimes, though, we get equations that look different. And the first thing you should notice about this line, the gray line that's now underneath my pencil, is that it is a perfectly horizontal line. That line never changes. And you'll remember from the video that you just watched that when you see a perfectly horizontal line, really the simplest thing to remember is that the y is always equal to some number. And if you look at the graph, since we're going up by ones, you can see here that the y value, no matter where we are on this line, is always equal to 2. So a nice way of thinking about this is, if you look at this point here, for example, this is the point 0, 2. So the x is 0, the y is 2. And over here we have the point negative 5, 2. Right? So the x has changed. It's no longer 0. It's negative 5. We've gone to the left. But we haven't gone up and we haven't gone down. The y has not changed. Negative 4, 2, negative 3, 2, negative 2, 2, negative 1, 2. Here's 1, 2. Here's 2, 2. Over here we've got 3, 2, 4, 2, 5, 2, 6, 2, etc. We can keep going. X's can keep getting bigger and bigger and bigger, and Y's and X's over here can keep getting smaller and smaller and smaller, but the Y will constantly be 2. Okay, so this is called the constant function, actually, and basically if you see a horizontal line, that's your answer. The one that they're trying to trick you with, we'll look at some of these other ones and what these ones look like later on. But basically, horizontal line is always going to be y is equal to some number. Keyword there being horizontal is always going to be y is equal to c, if you want, for a constant, or some people like to write y is equal to some number. Whatever you need to write in your notes so that you remember that particular type of line. Hey guys, welcome to exceptions in the straight line. Which of the following equations correctly defines the line shown in the graph below? So the interesting thing about this line is that at first glance you can see it has a slope, but you might notice that its initial value is located right there at the origin, which means that the b is equal to 0 for this line. So a couple of things. So if we're looking at which of these equations this might be, you can rule out a right away because a has a very clear initial value, right? Y is equal to ax plus b. There's your b. It's done. We know the b can't be 2. That would be up here. This one looks a little weird. We could isolate y by dividing both sides by 2, and we get this one when we do that. And that looks like it's possible. We can come back and revisit. And over here we've got x is equal to 2. I can tell you right away that that's not the answer, because in x is equal to 2, you'll remember from the videos, in x is equal to 2, the x is always a vertical line when we don't have a y. If there's no y in the equation at all, we get a vertical line. If it was y is equal to 2, we'd have a horizontal line at the y of 2, as we just saw in the last video. In this one, though, with the x, so basically I'm down to b and I'm down to d, and which one of these is accurate? Well, in order to calculate a rate of change, we need 2 points. And so I'm going to kind of look at my graph. I can see my 0, 0 here pretty clearly marked, and I'm going to kind of follow my line until I get a nice clean point, and I get that point right there. And that's the point 1, 2. And now I can calculate a rate of change using 0, 0 and 1, 2. So if I come over here, a is equal to y2 minus y1 over x2 minus x1. So I'll call this x1, y1, and I'll call this x2, y2, and I'm going to get a is equal to 0 minus 2 over 0 minus 1, which is equal to negative 2 over negative 1, which is equal to 2 over 1, or 2. Negative divided by a negative is a positive. And so I have an a of 2, and the only one with an a of 2, careful, it looks like it's got an a of 2, but not when you divide both sides by 2, right? The a is actually a 1 here, it's hidden. This is the one that has the a of 2. So your answer is D. It's got no initial value. We could write plus 0 if you wanted to see the initial value in the equation. Y is equal to 2x plus b with a b of 0, which we see clearly marked on the graph. Hey guys, we're looking at exceptions in the straight line. Number 3, which of the following graphs correctly represent the line defined by the equation y is equal to negative x plus 2? So we call this one an exception because a lot of people say, well, hey sir, I don't see the a here. There's no number in front of my x. The y is isolated, which it needs to be, but I don't see a number there. Well, you'll remember from the video you just watched that there is a number there. We just don't write it. We don't bother writing the number 1 when it's in front of a variable. So we can rewrite this as y is equal to negative 1x plus 2. So there is a rate of change. The rate of change is negative 1. The question then is, well, which of these 4 graphs represents this situation? So we're going to do a little trial and error, or a little process of elimination, I guess is a better way of putting it. And we're going to look at this equation. We're going to start off by looking at the b. The y is isolated. We have an initial value of 2. We know that that means that that line has to cross on a Cartesian plane somewhere where the y is equal to 2. So if you look at the 4 lines that we've been given, you'll see that this one passes through 0, 2, as does this one right over here. And letter D down here similarly passes through 0, 2. So these guys are all in the running as far as the initial value goes. But if you come down here, one of these guys is not like the other as the song goes, and you can see that that does not have an initial value of 2. It has an initial value of 0. It's passing through the origin, like the example that we just looked at in the last video. So it would have to be up here somewhere if it was going to match this equation. And so C is gonzo. There's another interesting feature on the A over here before we get too detailed, and that has to do with this negative. We know that negative slopes go down, and so whether it comes like this or like this or like this, whether it's super steep ski hill or a flatter ski hill, it's still going to be going down the Cartesian plane as opposed to one that's going to be going up the Cartesian plane. So these are positive slopes over here, and these are negative slopes over here. And if you look at the 3 that we have remaining, this is a negative slope, and this one here is a negative slope, but this guy over here is a positive slope. This one's going up. And so we can eliminate B. And that leaves us with these 2. And this is where it gets a little bit tricky, because we need to know, well, which one of these slopes is going to give us a slope of negative 1. And the only way to really determine a slope is to plug in some points to the formula that we know. And so it doesn't really matter which of the 2 we test. I can test this guy right over here and see what happens. So I need a second point, and I can pick any point I want on this graph as long as it's nice and neat. I'll pick this point right there. I know that that's 0, 2, and right over here, that's the point 1, 0. And so when I plug these numbers into the A equation, if I get negative 1 for my slope, I'll know that's my answer, and then that one must be wrong. But if I don't get the right answer here, then that means this guy must be the right answer. Let's see. A is equal to y2, so I'll call this one x1 and y1, and I'll call this one x2 and y2. So y2 is 0 minus 2. 0 minus 2 over 1 minus 0. I think you can see pretty quickly that the A for that one is negative 2. So we know he's wrong because we need a negative 1, which means this guy is right. But I'll show you how we can prove he's right. And we can do that the same way by using that A formula and picking 2 points. We know that this is 0, 2, and we know that this is 2, 0. And we can call this x1, y1, x2, y2. So again, I'm going to use that A formula. For this one was for D, but this one is for A. So 0 minus 2 over 2 minus 0. And that's negative 2 over 2, which we know is negative 1. And negative 1 is the number we know that's in front there. So A is our answer. Hi, this is exceptions in the straight line. This is question number 4. Identify the slope and the y-intercept of the following equation. And the reason that you might have difficulty identifying the slope and the initial value is because this equation has not been set up in y equals ax plus b. And you cannot read the a nor the b if you don't have the equation set up in this form. And we have to use the rules of algebra, transformational rules, they're fancy words, to say, hey, you know, isolate your y. Make your y be all alone. Sometimes the temptation is to say, oh, well, the a is 4. Look, there's a number 4 in front of my x, and the b is that negative 60 over there. So y is equal to 4x minus 60. And that's the temptation. This is what, you know, examiners hope you will do. It is wrong. You cannot do that, because we can't read those coefficients until, or these numbers, until we've isolated that y. So that's what we're going to do right now. The first thing that we're going to do is take a look at the equation. We're going to do some thinking about which numbers we're going to want to move and which operations we're going to need. And you can see I have a negative 60 that's being, you know, a 60 being subtracted from my y. And so at some point I'm going to have to add 60 to both sides. And you can see also that there's this 4x kind of being at the front here, which is another way of showing that it's being added to that 6y. This 4x is on the same side. It's being combined with it. It's being added there. We don't show the plus, but it's there. So we're going to have to subtract that guy. And then we've got this negative 6 hanging out in front of the y and being multiplied to that y, and we know to get rid of a multiplication we're going to do a division. So there are 3 kind of things to get rid of: that negative 60, the 4x, which is all one number, remember, and that negative 6. So I'll do them one at a time, and I'll use red just to show those operations. The first thing I'm going to do is I'm going to add 60 to both sides of the equation. I like to get rid of my constant first, the regular number first. It's the easiest one to move. The less thinking, the better. So I'll just put my pen down there. And that will then rewrite as 4x, he hasn't gone anywhere yet, minus 6y is equal to, now that went away. That was the whole point, right? We added the 60 so that that negative 60 wouldn't be hanging out next to the y, but whatever I do to one side of the equation, I have to do to the other, and 0 plus 60 is 60. Next up, I'm going to subtract 4x from both sides. Now, it's very important that you remember, you're not just subtracting 4. You're subtracting 4x, the whole term. This is one term of math, and we need to take the whole thing away. The number and the x, always. So that goes away, but it has an impact on the right-hand side of that equation. And so what's left underneath is going to be negative 6y, right, that's gone, is equal to, now negative 4x with that 60 there, they go together. So negative 4x plus 60. You could write that as 60 minus 4x, but we like to put the x term in front of the constant, so it's just a good habit to get into. Lastly, and some people stop here, but they forget that you've got to get rid of this number as well, the whole thing, including that negative. So we're going to divide that by negative 6, we're going to divide that by negative 6, and we're going to divide that by negative 6. All 3 parts. And when we do that, we're left with y, because negative 6 divided by negative 6 is positive 1, which we don't have to write, is equal to, now calculator time here, clear that up, negative 4 divided by negative 6, and that gives us positive 0.6 repeating, so I'll just 0.6 repeating. You make sure you keep that repeating. If you want to use a decimal, if you don't like fractions and you don't want to reduce this to 2/3, which is what it would be fractionally, then you can't just round that off to 0.6, because 0.6 is 6/10, not the same as 2/3. You need to keep that infinite decimal for calculation purposes later on. X stays there. Sorry, I shouldn't be writing plus yet. Positive 60 divided by negative 6, just in case you want to see it. 60 divided by negative 6 gives me negative 10. So it's not plus, it's minus 10. So I've isolated my y, and now that the y is isolated, you can see really quickly that the a and the b are very easily identified. There's your a, and there's your b. So to identify the slope, a is equal to 0.6 repeating, and if you're a fraction person, 2/3. And the b, or the initial value, is negative 10. And you can see right away, the a is not a 4 and the b is not negative 60. These are your answers. Okay, so the bottom line is, use your rules of algebra, isolate your y before you try to read your slope and your y-intercept.